Hello students, so we are gathered for warm-up series. This warm-up series aims to complete a whole syllabus, whole chapter in a very short time taken, less than 20 minutes or 30 minutes, with the most appropriate and most important topics, right? So today we are going to see about current electricity. Okay, so in this current electricity we are going to see about some important topics based on your board exams, and I request you to take notes along the sessions, which will be more useful while you are revision in your revision. Okay, so see about first topic, electric current. So this topic we are keep on studying from your small schools, small standards. Okay, so electric current is nothing but rate of flow of charges. So we can say a conductor is having current. A conductor is having current. So what does it mean? Means there is a flow of charges. There is a flow of charge. There is a flow of charges. So conductor, in the sense, at once I am saying conductor, we have to have the imagination of more and more amount of free electrons availability. More and more amount of free electrons availability. More free electrons availability. Okay, so these free electrons will keeps on will starts to move, and when these electrons when these charges starts to move, it contributes the current, and that is nothing but I is nothing but Q divided by T. Q divided by T. Actually the formula goes like I is nothing but dQ divided by dt. dQ divided by the rate of change of charge, rate of flow of charge. Okay, this is a correct statement. And coming back to, we can state this electric current only for constant in steady state. What is steady state? We are having constant flow of current. If we find different non-constant flow of current, which means we are having fluctuation in the charges. Once we are having more number of charges flow, and another time we are having less flow of charges, means we can redefine this current into this formula into another formula like dQ divided by dt. So we are going to limit the time taken to a zero time taken. So we can wonder, we might be wondering how the time can be zero. We are not going to limit the time to zero. We are going to limit the time taken for very small quantity. Let's say 0.0005 seconds or 1 second, 2 seconds. The meaning is, in that small duration time, how much charges are crossing the area. Let's say this is our area. In this small time taken, how much charges are crossing the area, and that is nothing but current, right? So current is nothing but rate of flow of charges, dQ divided by dt. And for non-steady state, for non-steady current means we can minimize, we can take the differentiation, putting the current for small duration. If we find small duration, we can find the average current, or we can say we can also say that for non-steady state we can find that current. Okay, coming back to Ohm's law. So Ohm's law aims that. So Ohm's law also we keep on studying from our 10th standard. Ohm's law, V is proportional to I. So what does it mean? Means if you are in a circuit, if you are having more number of current, definitely we will be having more number of voltage. Voltage will be higher. Okay, so voltage will be directly proportional to current. So if current increases, voltage increases. If current increases, voltage also decreases. Now listen, usually we haven't practiced that in physics. We haven't practiced. Whenever we come across a proportional symbol, we used to remove the proportional symbol, and we used to introduce a constant. So like that, here we are introducing a constant resistance. This is a constant. This is constant. Okay, V is equal to RI, which V is equal to IR, or else we can say also V is equal to RI. So now this formula can also be written in terms of R is equal to V by I. R is nothing but just we are rearranging the formula. So from this, what we can infer means, if current increases, definitely voltage will increases. What I am asking is, if current increases, do the resistance increases? If current increases, do resistance increases or decreases? So nothing will happen to resistance. That's the answer, because resistance is a constant. Okay, this is purely based upon its material and some other external factors, and the resistance is independent of voltage and current. But current is dependent on voltage, and voltage is dependent on current, but resistance is independent of either quantities, voltage and current. This thing we have to keep in mind, right? Okay, so then coming back to graph. So we all know that slope will give, see, listen, R is equal to V divided by I. V divided by I is nothing but a slope, okay, in a slope of IV curve, IV graph. This is IV graph. In this IV graph we are having a straight line. In this straight line, if we are taking some slope, this slopes will give the resistance value, because R is nothing but V divided by I, right? So this slope will give rise to resistance value, and this is something we have to keep in mind. Coming back to next topic, resistivity of a material. Resistivity of a materials is purely based upon its material. We used to define a material. See, from Ohm's law we know that V is proportional to I. From here V is equal to I, or we are introducing some constant R. I am saying that R is independent of voltage and current. Then what depends on resistance? Resistance depends on length and the area of a conductor. Okay, so if length increases, resistance increases. If area decreases, resistance increases. See this logic. If you are keep on increasing the length, if you are keep on increasing the length, the resistance will be increasing correspondingly. If you are keep on increasing the area, what happens means, so we are making the more availability of charges to move. We are making more space. We are having more channel. We are making more space to flow more number of charges. Okay, so here, see, here more number of charges can be flow, but here we can see there will be a less flow of charges comparatively, because our cross section area is lesser. Okay, so from this we can say this, the resistance is nothing but opposite to conductivity, right? So let's see all this in later. Resistance will be proportional to length, and resistance will be inversely proportional to area, right? So from here we can define that R is proportional to length divided by area. Okay, again, if we have to remove the proportionality symbol, so to remove this proportionality symbol we have to introduce some constant. What constant? Proportionality is constant, and that proportionality constant is resistivity, L divided by A. So from here we can say that resistivity will be equal to RA divided by L. Okay, so this is resistivity and this is resistance. R is nothing but resistance, and the area, A is contributes area and its length of a conductor. This is cross sectional area and this is length of the conductor. Okay, so I think this will be clear to you. Then this is all about resistivity. And coming back to units, so units we have to keep in mind whenever we come across any formula. We have to be conscious on units also. So units of a resistivity, will see resistance or resistance value, unit of resistance ohm, and area unit of area meter square, unit of length meter. So meter and meter square will cancel one. So at last we will be having ohm meter as a SI unit. Okay, right. So I said that inverse of resistivity is nothing but conductivity. If your conductivity is inversely proportional to resistivity, and resistivity is inversely proportional to conductivity. If thus we can take inverse of the resistivity, we can have conductivity. Okay, that's it. So again the same formula can be taken inverse, and that's it. So and coming back to current density. So current density is a small topic. See, I am saying that current is a do you know current is a scalar quantity or vector quantity? Current, what quantity is current? Either scalar or vector. Okay, so this current depends on time. Based on some places we are defining current as a, some places we are defining current as a scalar quantity, and in some places we are defining current as a vector quantity. Okay, so in most of the cases, generally we are taking current as a scalar quantity, though they are having directions. We are considering as a scalar quantity due to some factors. Let's discuss those things in any other different sessions. Okay, so current is a scalar quantity, but current density is a vector quantity. Current density is a vector quantity, right? So current density is a vector quantity. Let's confine this. Okay, so we are having some formula like F is equal to ma, I is equal to q by d, like that. We are having some fundamental formula like current density is nothing but current flowing per unit area. Current density is nothing but density, you know, how much charges are flowing per unit area. That's it. So for unit area, how much charges are crossing the cross section area. That's it, and that's the thing for current density. coming back to SI units, we know that current is nothing but unit of current is ampere and the unit of area is meter square. While by getting denominator to numerator, we can have m square to m to the power of minus 2. Okay, so next question, next topics listen. Vector form of Ohm's law. So I said that current density is nothing but I divided by A. Current density is nothing but I divided by A. Then how comes this formula? Okay, so let's explain that. So first of all, we can focus on current. This current can be written as I is equal to V by R. I is equal to V by R. I is equal to V by R. And this from second chapter, from electrostatic potential capacitance, we know that electric field is nothing but potential difference. Electric field is nothing but potential difference. Electric field is nothing but potential difference. Here we can say that potential difference can be written as ED. ED, D is nothing but distance travelled by the charge. What is the distance travelled by the charge? It's the length of the conductor. It's the length of the conductor. So that we can say, instead of writing, see, I'm going to focus on current and load. In that current, I'm going to focus on voltage. So voltage, if you are focusing, means we can say that electric field times the length of the conductor. Okay. And what about resistance? We know the resistance value is R is equal to rho L divided by A. We are going to include the same quantity, rho L divided by A. Okay, now we are going to cancel similar terms. So while cancelling similar terms, L can be cancelled. So after that cancellation, what we can say, I will be equal to E A divided by rho, E A divided by rho, right? Okay, so now we know about current. Okay, now we know about we are going to take this current into current density. J will be equal to E A divided by rho divided by A. So now we are having similar terms A and A. You can cancel it out, and current density can be written as E divided by rho. And this is one of the important formula, as J is nothing but rho into E. What is rho? What is rho and what is a sigma? Sigma is nothing but conductivity. Sigma is nothing but conductivity, and rho is nothing but resistivity. I said that inverse of conductivity is nothing but resistivity, inverse of resistivity is nothing but conductivity. That's it. The same logic here applies here. Okay, so we can say that J can be written as, which means the current density can be said as electric field times divided by rho. Rho is nothing but resistivity, and if you are focusing 1 divided by rho, we can say that inverse of resistivity is nothing but conductivity, so that we can also include sigma. That's it. Okay, so no other any other big thing here. Coming back to drift velocity and relation with current. So this is something we have to, very important in this chapter, something we have to focus. Okay, listen. First of all, drift velocity, we have to know about what is drift velocity. Drift velocity in the sense, see, in a non, whenever in a external field is not when external field is 0, when external field is 0, what does it mean? Means we are not applying any potential difference. We are not applying any potential difference. Okay, so let's say this is a circuit. We are not applying any potential difference. In this case, what happens to the conductor? What happens to the conductor? See, there will be the movement of free electrons. There will be a lot and we will be having more number of free electrons availability, and those free electrons will be moving very random motion. It will have random motion, right? So overall, if you are considering overall, the random motion of the velocity charge will be equal to 0. Why? So any of the velocities from one point to another point will be cancelled out by another velocities either in this conductor. Okay, so what does means, if you are having this conductor, okay, we are having a conductor, the thing is, the charge will used to move like random motion. It will move here and here and there and move on, and at last it will be coming back to its some original position. So precisely we are having speaking in a macroscope scale. See, the displacement can be related to almost to 0. Displacement is almost related to 0. Once displacement is related to 0, displacement is considered to 0, we can declare that the velocity of a free electrons will be equal to 0, because there is no displacement, though it is traveling along the though the charge is traveling throughout the conductor, it is coming back to its original position. so that we can say that the displacement will be equal to, we can relate it to 0. Once we are clear that the displacement is equal to 0, we are sure that there will be no velocity. Velocity also will be equal to 0. Okay, so that's the thing, right? So once we are clear about this, then what is drift velocity? Okay, you might wonder what is drift velocity. Okay, drift velocity is nothing but we are speaking this in the absence of external field. In the absence of external field, when no battery is connected. What happens when battery is connected? When battery is connected, we are having drift velocity. Then what is drift velocity? So drift velocity means, listen, this is a conductor. I am saying that some potential difference is included. If potential difference is included, there is an inclusion of electric field. We are including some electric field, right? So we are placing the electric field in the conductor. We are placing the conductor in the electric field zone. Okay, so in that situations, what happens means, so conductor means here we will be having positive charges. Plate, like just imagine whenever you are seeing that electric field lines are coming from left to right, just consider there is a positive plate over a left side. Okay, so what happens from the electrons from here will start to migrate. Electrons from here will start to move towards the plate, right? So electrons from here will start to move towards the plate, and it will be reaching one end to end A to end B, like end B to end A. Okay, so here the electrons here, can we say the net velocity will be equal to 0? No, here we cannot say the net velocity will be equal to 0, because there is a displacement. From B to A. That's a displacement from B to A. In the absence of external electric field, we don't have any displacement, right? So we don't have any displacement, so that we can say that there is no displacement and there is no velocity. Here we are having displacement, so since we are having displacement, we can say that there is some velocity is incorporated, and that velocity is nothing but drift velocity. Okay, here the velocity is not equal to 0, and that velocity is nothing but drift velocity, right? Drift velocity, simple thing. Next, and okay, it is understood that whenever external electric fields are introduced in conductor, there is a drift velocity is incorporated, included. Okay, so electrons will have some drift velocity. Okay, so how can I measure the drift velocity? You can ask that, how can I measure the drift velocity? Okay, so for this we can have some small derivations. Okay, don't panic about derivations, just look into the steps, and just you have to focus on results alone. Drift velocity, guys, listen, whenever you are seeing, please make notes out of the sessions, not this sessions, any sessions. Whenever you are looking for any sessions, any topics, any discussions, any lectures, please have a note and pen, paper and pen with you, and please note something in your paper. Whatever you are getting, whatever the things it's getting into your mind, just put it in your paper at once. Right, now we are going to have the drift velocity derivations. We know that drift velocity, see, whenever in a conductor there is a charge, so this electric field is moving from left to right, so the charge will also, considering the charge is positive, this charge will also experience some force. Experience the force. These things we keep on studying from first chapter. Okay, whenever in the external field, if you are placing a charge, and that charge will experience some force, either towards or opposite to the external field, we can consider the force will be equal to QE. From mechanics, I know that the F will be equal to MA, right? F is equal to MA. Here I am going to arrange that A is nothing but QE divided by M. A, this is nothing but acceleration. This acceleration can also be written as velocity divided by time taken. I am going to write this acceleration as velocity into time taken. Okay, velocity into time taken. Here I am going to include small changes. Here this time taken can be written as relaxation time. What is relaxation time? What is relaxation time? The relaxation time is, see, I said that in a conductor the charge will be keeps on moving in a zigzag manner. In zigzag manner, will be the collision, because see, there is in a conductor we are having multiple charges. Okay, if a charge starts from here, it has to move from B end to A end. If a charge starts from B end, it has to be it will be moving till NDA. So till NDA, in the path, the charge will come across multiple number of collisions, okay, because the conductors having more number of charges. So while coming from B to A, it will be having collision with so many charges, okay, so many charges will be having collisions. After that, it will be reaching at NDA, okay. I am saying that in these two collisions, from here, focus here, from this point to this point, it is having some non-collision path. After here is a collision taking, and here also collision is taking place, and here also collision is taking place, and mean you just focus on mean duration, and thus duration is nothing but relaxation time, okay, which means the successful the time between two successive collisions, the time between two successive collision, right. This is nothing but relaxation time. Okay, I am going to include this time as here, okay. Drift velocity, this is not see, acceleration is nothing but velocity divided by time taken, and that this is not about normal velocity. This is drift velocity, and that time taken is not normal time taken, that is relaxation time. So that we are going to include tau. This relaxation time is having some new symbols, tau, okay. So this tau we will be using in mechanics for torque, and here as well we are going to use that for relaxation time. The time between two successful collisions we are going to define as relaxation time. And now see here, we want drift velocity. So drift velocity can be written as QE divided by M into tau, and this is, guys, the most important topics, the most important formula. QE divided by M is equal to tau. So then what does this charge, what is this negative symbol means? This negative symbol means the charge will be moving opposite to the direction of electric field. The charge is moving opposite to the direction of electric field. Listen, here we are having electric field towards left to right. Here we are having electric field to left to right, but our charges are moving from right to left because positive charge. Now our charge is negative charge, so the negative charge will be our negative charges will be attracted by positive charges, and that will be moving opposite to the direction of electric field, and that is negative symbol, right? Okay, this negative symbol what does means? Charge moves opposite to electric field, right? Okay, done. Next, current. So this current is nothing. Here we know that drift velocity, we completed drift velocity. Then we have to know about this current formula. What is current? Okay, current. We can also define current. Listen, I is nothing but Q. I is nothing but dq Q divided by t. I is equal to Q divided by t. We are focusing on Q. Q is nothing but Q is equal to NE, and this T is nothing but see, listen, the conductor, it's a length of the conductor. From here, what the time taken to reach end B to NDA, and that is the time taken. We can say that speed can be written as L divided by T, and here T can be written as L divided by V. Keep as it is, and come back to Q. Okay, that's it. In drift velocity, in current can be written as NE divided by time taken. This time taken can be written as L divided by D. T is equal to L divided by velocity. L divided by drift velocity. While using this drift velocity upward, NE dV divided by L, right? So what I am saying that this is number of charges in a conductor. This is number of charges in a conductor. In a per unit area alone, per unit volume alone. N is, listen, this N is nothing but number of charges per unit volume. Okay, fine. But we are having our conductor with some length, and we are having our conductor with some area. So how we can define the volume? We can define the volume as area into length. Okay, when we are substituting this area into length, we can say this term, what does it defines? The number of electrons in a unit area, unit volume. This is, let's say this is a unit volume. Let's say this is a unit volume. Let's say this is a unit volume. The number of charges occupied in this unit volume is taken as n. If you wish to take the total number of electrons in this whole conductor, we have to add the volume of the whole conductor. Adding the volume of whole conductors, AL NE dV divided by L. So cancelling AA, LL. So as a result, what we are having, I is equal to A N E dV. Avan. Okay. In Tamil there is a, if you want to if you wish to memorize this term, I is equal to avan. Naan avan illai. And the mari you can say that I is equal to avan. Okay, right. So this is all about current in a conductor while external field is applied. Then what about current density? This is I am giving to you. Okay, what you can do is, see, we know that current density is nothing but I divided by A. I divided by A. You can include this instead of I. You can include this formula. Instead of dV, you can include this above formula. If you substitute those two formulas, you will be having this formula. Okay, this is just, you can check it out. Next formula, conductivity. I said that conductivity is nothing but reciprocal of resistivity. Okay, this is also, it's your part. Just go through. See, from where this conductivity comes from, we know that current density. Conductivity is nothing but, we know that current density is nothing but conductivity times the electric field. Just put conductivity from here. Conductivity can be written as current density times the electric field. Put the formula for current density, put the formula for electric field, and you will be having this formula. Right? That's it. So we can move on to next topic. Mobility. Mobility is a special term as drift velocity. Okay, mobility is a special term as drift velocity. So we can relate mobility, electric field, and drift velocity in a single formula, like mu is equal to V divided by E. Drift velocity divided by electric field. This is nothing but drift velocity. This is drift velocity, and this is electric field. And this is electric field, right? Okay, this is something, see how easily the electrons can move in this conductor, that contributes the term mobility. Okay, so mobility is nothing but how easily or how difficult the electrons is going to move in the conductor. Okay, so how we can measure, and that is, so this is how is I am saying the topic definitions. Mobilities can be written as how easy the charge moves in a conductor, right? Okay, then how we can quantify it? We can quantify by using drift velocity and electric field lines. So mobility can be written as drift velocity divided by electric field lines. Okay, then we are having some limitations for Ohm's law also. So we are having some limitations for Ohm's law. See, we keep on seeing this for these things from Ohm's law. See, these things are under the topic Ohm's law. In this Ohm's law, though we are having multiple privileges, we are having some difficulties. We are also having some limitations over Ohm's law. What are the limitations? This Ohm's law is well defined for only at constant temperature. This Ohm's law, which is what is Ohm's law? V is proportional to I, V is equal to IR. This Ohm's law is well defined only for constant temperature. Constant temperature. If we keeps on increasing the temperature, if you keep on varying the temperature, we will not have the proper Ohm's law obedience in the conductor, right? So we want to have constant temperature. Okay, so if the temperature is getting exceeded to the assumed needed temperature, we will be having fluctuations in the Ohm's law. For example, we will be the direct meaning means whenever the current is increases, voltage should be increases, which is nothing but voltage is directly proportional to current. Voltage is directly proportional to current. Okay, so if current increases, voltage also increases. If current increases, voltage also increases. But this voltage increases only to a appropriate temperature only. Beyond the temperature, beyond the appropriate temperature, we will be having fluctuation in the Ohm's law, which means beyond that there will not be directly proportionality symbol for current and velocity. So beyond this time, beyond this scale, you see the current is increasing, the voltage is slightly getting constant, right? So this thing is one of the difficulties and one of the limitations over Ohm's law. And the second case coming, it's about semiconductors. So semiconductors, we are having, we will be talking about those things in semiconductors chapters. We are having some devices called diode. What does this diode means? This diode will conduct the current in a positive terminal, which means if the current flows from left to right, it will be conducting. If the current is flowing from right to left, it will not conduct, okay? But it will conduct very feeble current only. It will conduct very feeble current only. In the oppositely, if the current is passed from left to right, right to left, okay? Feeble means very light current, very mild current, okay? Okay, in that situations we cannot go for the proper Ohm's law, okay? So in semiconductors we cannot expect the proper Ohm's law there. So if you are increasing the current, there will be a decrease in, there will be the increase in voltage as well, but it is that is a different proportionality, okay? It will be increasing voltage, it will be having a current, corresponding current increases, and in negative direction, if you are increasing current, it will be having increase in voltage in a corresponding quantity, okay? We will not have the directly proportional symbol. And another case, we are having some gallium and arsenic. This is also a semiconducting materials. In that materials, if we are giving, if we are expecting the Ohm's law for directly proportional, and that will not be happen, right? So if you are increasing voltage, we will be expecting the current should be increases, which means we will be expecting, if a current increases, we will be expecting to increase in the voltage, but that will not be happen. That will be happen for some times, okay? For increase in voltage current, we will be having increase in voltage, but after sometimes we will be having decrease in voltage for increase in current, okay? For increase in voltage, decrease in current, and we will be having some graph like this. From this graph, we cannot say that that's a directly proportional to voltage and current, okay? This character is purely based on the material's nature, and we can say that Ohm's law will not obey. Ohm's law will have the deviations for semiconductors and non-appropriate temperature, okay? So this is other small limitations in Ohm's law, okay? And this is nothing but, and this topic is temperature dependence of resistivity. This is some interesting topic. We can say that what we are seeing, that resistivity is a character of a material. Resistivity is a character of material. It's an intrinsic property. Moreover, it's an intrinsic property. It's an intrinsic property. Okay, so from multiple experiments, what we are finding that the change in resistivity of a material is directly proportional to original resistivity. The change in resistivity is also proportional to change in temperature, okay? So while we are packing these two formula into a single formula, the change in resistivity will be proportional to initial resistivity and the change in temperature, right? Okay, and this thing can also be written as, this is change in resistivity. If we want the overall resistance, actually initially we are having rho naught. Now we are having some change in resistivity. We are having some increase in resistivity due to some temperature change. Finally, this will be the resistivity of a material. This is the final resistivity of material. Final resistivity of material. All right. Now, what we can say that just we can, if you want final resistivity of the material, you can add the initial resistivity of a material into the change in resistivity. Initial resistivity rho naught plus change in resistivity rho naught del T. Okay, so the rho naught del T, this we have to remove this proportionality symbol. To remove this proportionality symbol, we are going to introduce a small symbol like alpha. Alpha is another constant. It's based upon its temperature coefficient of a material. Okay, how the material, how much it can absorb the temperature, and that contributes to the constant alpha. So del rho is equal to alpha rho naught del T. Okay, so we can include those things here, those stuffs here, and we can take constant common terms common. Okay, rho naught plus alpha del t, rho naught plus alpha del t, and this is a final formula. Okay, so I don't prefer you to mug up the formulas. Please keep an eye how the formula is getting developed. Okay, so while you are, if you need any formulas, just go through the steps quick and get your formulas as soon as this is your first formula. And next thing, temperature coefficient of a resistance, and we are going to I said that alpha is nothing but temperature coefficient. Okay, just now I said that alpha is nothing but temperature coefficient. What we are doing that we are going to just rearrange those things to know about alpha. So if you rearrange this, we will be having these formulas, and please keep in mind that the unit of alpha will be equal to temperature inverse, which means Kelvin increase or Celsius increases, inverse of Celsius, inverse of Celsius or inverse of Kelvin or inverse of temperature, and that will be the unit of alpha. And here we are having some 3 different graphs for metals, semiconductors and alloys. So metals, if you see, means we will be having some increasing curve, and for insulators and semiconductors we will be having negative temperature coefficient, which means negative, we will be having inversely proportional curve, and for more alloys we will be having straight line, right? So for these things we have to know about. If we increase temperature, what will happen to the resistance? If we increase temperature for in a conductor, in a metal we can also say as conductor. In conductor, if you increase temperature, we will be having decrease in conductivity. Because the bonds will be breaking in the conductors, and there will not be any shift in charges, free electrons movements. Okay, in conductors, if you are increasing temperature, we will be having decrease in conductivity. At once I said there is a decrease in conductivity, you may think that there is an increase in resistivity, and that's right. Okay, when we in because conductivity and resistivity are oppositely proportional, right? Whenever we are getting increase in temperature, we are having increase in resistivity with some proportional, right? And that for that we are having increasing curve. And this case is different from semiconductors and insulators. What happens to semiconductors and insulators means, in semiconductors and insulators, if you keeps on increasing the temperature, the resistivity will be, the conductance will be getting increased. That's the, see, listen, in conductors and semiconductors will be having less amount of availability of free electrons, right, compared to conductors. In those conductors, in semiconductors and insulators, if we are increasing the temperature, what it will make the electrons to gain the energies, and those free electrons will be having more energies, and it will be shifting very fastly. Okay, and there will be the more number of conductions. For insulators and semiconductors, if we increase the temperature, we will be having good number of conduction. We will be having good number of conduction compared to previous case. So if I am saying that the connectivity is good, what you can say that if conduction is good, if the connectivity is good, there is a bad connectivity, there is a poor in resistivity, right? In semiconductors and insulators, we can say that, for increase in temperature, there is a decrease in resistance. For increase in temperature, there is a decrease in resistance or in resistivity of a material. Okay, for semiconductors and insulators, for increase in temperature, we are having decrease in resistivity, so that we are having inversely proportional curve. Okay, and alloys is a different case. Okay, alloys is a different case. If you are getting alloys is nothing but we are mixing up 2-3 metals in a simple, for example, silver and copper, gold and copper. We can say that gold and copper. Okay, so gold plus copper. Okay, in this is a metal, this is an alloy. If you are getting if the temperature increases, the resistivity will be increasing proportionally with some in a linear curve. This is something you have to know. Look into these 3 graphs. These graphs are important. Next thing, electric energy. So before going to electric energy, I like to introduce 2 formulas for power. And power is nothing but VI. P is nothing but V, power, voltage. V is nothing but voltage, and I will be equal to current. I think you might know this formula from your 10th standard, but just keep it as a revision. Power is nothing but VI. Okay, this is a fundamental formula. Okay, if we are introducing the Ohm's law here, if we introduce Ohm's law here, we can either change the formula as V square divided by R or I square divided by I square R. Okay, and this is the first thing we have to know. At once we are well known about power, we can say about energy, work done. See, listen, work done can be written as, work done is nothing but power is equal to work done divided by time taken. Okay, from here we can say work done can be written as power into time taken. That's it, right? So work done is nothing but power into time taken, and whatever the values we are having for power, just if you put it power we are having three formulas. Power P is equal to VI. Okay, and that will, if time is included in that power, we can have the work formula, and we are having another formula I square R. If you are including the time to the power formula, we can have the work done formula, and we are having V square divided by R. We are having V square divided by R for power. Okay, if you are including the time to the power, we are having that work done, right? And that's it, guys. Work done is power. These are the basic formulas we have to know. And coming back to cells, EMF and internal resistance. EMF is nothing but the internal energy in the sense we can see cells is made up of some chemical reactions. Okay, and those chemical reactions will contribute the potential difference, Let's say here plus and minus. This EMF is nothing. This EMF will contribute the charges here. We are having multiple charges here. This potential difference will contribute the charges to the movement, and that charges will have the circulation in form of current. Okay, so this is EMF. This is nothing but EMF, electromotive force. Okay, so we have known about electromotive force. Then we have to know about resistance. Okay, whenever we are manufacturing a cell, we have to consider the internal resistance, because no cell in the universe is having with zero internal resistance. Okay, an ideal cell, only the ideal cell. See, whenever we are going for ideal case, that might not be existence, right? So actually we don't have any ideal cells, but whatever the cells we are having, it will be having some internal resistance. We cannot compromise, we cannot avoid that internal resistance. Okay, so internal resistance always comes within cells, and this is a structure. And I have to say about another term, terminal velocity. Terminal velocity is different from the EMF. So EMF is a potential difference having in the cell. Okay, terminal voltage is nothing but, see, as a cell, it will be having some internal resistance. Okay, in this terminal, overall in this cell, what is the terminal potential? Okay, to know about that terminal potential, we are having a standard formula, E minus IR. This is only for discharging cell. Then what about charging cell? Just we can just flip the sign alone. Then see, you have to know about what is discharging cell, what is charging cell. Listen, if you are having some cell, okay, usually current flows from positive terminal to negative terminal. This is cell, this is resistance. If you are having current in this direction, this is discharging cell. What is discharging cell? The cell keeps on decreasing its potential. See, we are buying some voltage, we are buying some battery for 1.5 voltage battery, 3 voltage battery for our remote or for our wall clock. Over a period of time, the battery is dropped to zero potential. Okay, after that it will not contribute any potential difference. What does it mean? Means our potential difference, our battery keeps on discharging its energy. Okay, so this energy keeps on decreasing over a period of time, and that can be said as discharging cell. Then what is charging cell? Charging cell can be related to our battery, our phones. Okay, once we are seeing the low battery numbers in our phones, we are going to plug in the chargers, and our phones will be having charging. Okay, there what happens? The same cell, I am saying that this is our battery. See, battery is different from cells, that is different case. Here the current is flowing from here to charge the cell. The current flows from opposite to the rest of discharge cell. This is to charge the cells. Okay, this is for charging and discharging cells. For this case we will be having terminal potential. This is terminal potential for AB. Terminal potential of AB will be equal to EM of the cell minus IR, current in the circuit, into resistance, internal resistance. This is internal resistance. Okay, for a charging cell, the terminal potential will be equal to the terminal potential will be equal to EMF of the cells plus current, because we are having direction opposite to the discharging cells, plus IR. Okay, this is the small thing we have to keep in mind. Okay, have a look over this. Okay, let's move on to next topics, and this is cell. We are well known about cells combinations. See, as simple, if you are having multiple cells, we can just add. We are having multiple cells connected over a series connections. We can just add the cells alone. So cell equivalent will be equal to cell 1 plus cell 2 plus cell 3, and EM of the cell 1 plus EM of the cell 2 plus EM of the cell 3 plus, and it will be, keeps on going n number of cells. Okay, if you are having n number of cells connected in series, we can just add up and we can have the equivalent cells. If you are having n and focus on cells, each and every cell is having its internal resistance. So while calculating the equivalent EMF, we have to calculate the equivalent resistance over an internal resistance, right? Then we have, see, this cells will have some internal resistance here, this cell also will have internal resistance there, and those resistance are connected in series. You are well aware that whenever the resistance are connected in series, we can just add. That's it. Okay, so instead of connecting this n number of cells, we can add only one cells which will be equivalent to that multiple cells. Okay, that is nothing but equivalent EMF of the equivalent cells, and and again we can introduce a small internal resistance, and that resistance will be equalize those n number of cells, and that is nothing but R equivalent. Okay, so to find this R equivalent, it is enough to add this every resistance. To find the equivalent EMF, it is enough to add this EMF of the every cells. Okay, this is all about series connection. Then what about parallel connections? So parallel connections, we are having some formula. So EMF, the E equivalent divided by R equivalent will be equal to E1 plus R1 plus E2 plus R2, and keeps on going. Here we are having only two branches, so it is enough to add only two cells. Okay, I have to mention the small thing alone. See, listen, here we are having same terminal, we are having same positive negative in the same direction. Here also we are having positive negative. Nothing much to be worried. But if you are having the polarities in a shifter manner, if you are having polarities as a shifter manner, for example, first cell is having like this, and second cell is in the opposite direction, means here what we have to do means we have to just change the symbol of a cell alone. Okay, here also we cannot use the E1 plus E2 plus E3. Here also we cannot use the same thing. Here we have to use the formula in a modification with a small modification. So here let's say E1, this is E2. The E equivalent will be equal to E1 minus E2. E1 minus E2, because the polarity of the cell is changed, right? So that we have to also change the symbols. Here also we are having same terminal plus minus, so that it is enough to add both the cells. But if we are having either polarity in a different manner, okay, with respect to another cells, we have to change the symbol. Here if the second cell is in the opposite polarity, we have to change the symbol to minus, right? This the thing you have to keep in mind, and that's it. This is all about finding the equivalent resistance, then finding the equivalent cells, EM of the cells, and finding equivalent resistance. We know that the resistance are connected in parallel. While in parallel connections, we are known that 1 divided by R equivalent will be equal to 1 divided by R1 plus 1 divided by R2. Okay, while by using these formulas, we can sort out the internal resistance also, right? So just go through these formulas, and after that we can confine with terminal voltage with this two terminals A and C. In these two terminals, we are having overall EMF will be equal to E equivalent minus IR, right? So that's it. And coming back to Kirchhoff's law, it's we are having Kirchhoff's law in with two terms: Kirchhoff's voltage law and Kirchhoff's current law. Kirchhoff's current law is nothing but in a junction we don't have any charge dissipation. In a junction we don't have any charge dissipations. The number of current entering the junctions will be equal to the number of current exiting the junction. This is the only case, which means I can say that the net current in the junctions can be equal to 0, can be not, will be equal to 0. Okay, the net current will be equal to 0. Okay, where? In junction. What is junction? A point where the multiple charges, multiple wires are connected in a particular point. Okay, and junction is different from node, right? Okay, this is Kirchhoff's current law. And coming back to Kirchhoff's voltage law, Kirchhoff's voltage law can be put in place where the circuits have an open circuit, in a closed circuit, in a loop. Okay, in whatever the case, we can use the Kirchhoff's second law, Kirchhoff's voltage law. So here, what is in this, by using this Kirchhoff's voltage law, we have the privilege to find the potential difference. Okay, and this Kirchhoff's law aims to have them. This Kirchhoff's law is basic thing is the net is equal to 0. Net voltage is equal to 0 means the net voltage over a closed loop is equal to 0. That would be correct. The net voltage over a closed loop is 0. The net voltage over a closed loop is 0. Okay, this is the thing we have to keep in mind. So you see how it works. Taking a chart, let's see, listen. Current flows from different from high potential to low potential. Please consider point A. Let's say in point A we are having potential A. Okay, so we are moving from point A to point B, point A to point A again in a closed loop, and we are going to frame the voltage law. Okay, just listen. First thing we have to say voltage at voltage at point A. Move from A point to here. In this cell we are crossing the higher terminal. In this point we are crossing the higher terminal. See, whenever you are crossing a cell, our potential will be increasing or decreasing. If you are crossing the higher potential, our potential will be increasing to a value of the cell. If you are moving, if you are crossing the lower cell, which means a lower terminal, our potential will be dropping to the value equivalent to the cells. Now I am having VA potential. While crossing the cells, I'm crossing the higher potential at the end. I'm crossing the higher potential at the, so that our potential will be increasing by the value of cells. So VA plus E1. Okay, and come back to after cells, we are going to cross this resistance. This resistance, what it will do means it will drop the voltage to some quantity. Okay, and what will be the potential drop means? What will be the potential drop means? The potential drop will be equal to I into R1. Okay, so I is the current flowing in the circuit, and this is the potential drop. V is equal to IR. Okay, this resistance will drop the voltage of IR1, right? So here minus IR1. Okay, see, since the potential is dropped, I am including the symbol I. And another thing, I am moving in the direction of current. The current is moving in the direction of, I am moving in the direction of current. If we are moving opposite to the current, opposite to the direction of current, if you are moving opposite to the direction of current, we have to include plus. You have to keep in mind that this thing. Okay, come over a resistance and come to resistance 2. In this resistance, we are crossing the lower terminal. Since the lower terminal will drop our voltage to the value of cell. Okay, so minus E2, and coming back to the resistance, this resistance will drop the voltage. This resistance will drop the voltage IR2 to the value of IR2 Since we are moving in the direction of current, we can say that minus IR2, and while reaching here, it will be the potential of VA. While reaching here, and this will be the potential of VA. Okay, so cancel VA. So balance, if you are looking in these two terms, it will be having this, right? E1 minus IR1 minus E2 minus IR2, and that will be equal to 0. Okay, first time if you are looking into this thing, you will be wondering how this happens. I'm little bit confused. Okay, this is first time if you are looking into this scenario, we will be having some little bit confusions. But trust me, if you are come across 2 to 3 times like a same thing or same problem, so if you are working this 2-3 problems, you will be having like familiar things with this topic. You will have a familiarity with this topic. Next thing, last and final topic, Wheatstone bridge. We are having some great derivations for Wheatstone bridge. As far as time being, we are not looking for those derivations, we are just looking for the result alone. So when we can use the Wheatstone bridge, whenever the Wheatstone, there is a condition. If this condition happens, we can use the Wheatstone bridge result. What is the condition? The condition is, this is a Wheatstone bridge setup. This is a Wheatstone bridge setup. In this setup, we want to have potential A, potential B at same potential. We want A, B and D at same potential. Why? Since if we have the potential B and if you have the potential B and the potential D with the same potential, okay, if you are having a point B point and B junction and D junction with the same potential, we will not have any current in this mean galvanometer. We will not have any current in the galvanometer. So in this scenario, we can use the galvanometer Wheatstone bridge conditions. Okay, so whenever you are looking into the circuit, just look into the potential of B point and D point. Just look into the potential for B junction and D junction. Just verify it whether it is potential is equal. Whether just verify whether the potentials are equal or not equal. Okay, if it is not equal, the bridge is not balanced. If this is equal, the bridge is balanced. It is a balanced condition. Balance. What happens if the balance condition? If the condition is balanced, if you are having same potential, there will not be any transformation of charges, which means there will not be any current over a circuit. So galvanometer current will be equal to 0. Galvanometer current will be equal to 0. In this case, we are going to say that this Wheatstone bridge is balanced. Okay, in this case, we are going to say that Wheatstone bridge is balanced, and for such scenario, we are going to have a privilege to use this resultant. What is the resultant? Taking the ratio of upper two resistance and taking the ratio of lower two resistance, and those two resistance should be equal, and those two resistance should be equal. Okay, so listen, we are having R1, R2, say R2, R4 and R1, R3. Just take the ratio of upper two resistance, which means R2 divided by R4. Take the resistance of lower two resistance, R1 divided by R3, and that should be equal to 0. And this is the condition for Wheatstone bridge. Okay, so this and this, it's an same formula. Don't get confused for small things. Okay, this is the condition for Wheatstone bridge. This is all about Wheatstone bridge. So what is the use of this Wheatstone bridge? You can question why these people are using this Wheatstone bridge concept. Okay, by using this concept, we can find the unknown resistance in a circuit. If you are not knowing this V3, we can find the V3 resistance. If unknown, we could find it. That's the thing, right? Okay, I think these are all the things we have seen. We have seen some important topics in the current electricity. I think those topics are clear. If you are having any doubts or any concerns over the sessions, please drop your comments in the comment sections, and I will be addressing those things. Okay, and at the end, I am having some 2 to 3 notice for you. This is all about fast track batch. So Xylem is introducing some courses called fast track batch and VETRI and Thalapathy. So I will be explaining those batches right now. Fast track batch is not only for the persons who is opting for 2026 NEET. This fast track batch will provide for them with good preparation. So we will be compressing the whole syllabus in a very short manner, and this fast track batch will have multiple more and more practice sessions, and this fast track will have grid-in battles, and this fast track batch will have an alternate test series at the end of the courses. Okay, so these are all the things will be available, and here we are also having some recorded sessions. Okay, you can use those things after for any of your doubt clarifications, and in futures also. Okay, we are having recorded sessions, and we are having the most important thing is previous year question discussions. Okay, see, for after completing each and every topic, we will be having previous year questions discussions at once the topic is cleared. Okay, so these are in this course we are having everything compressed here, and the price of the course is 8,499, little 8,500. Okay, why I am saying here means right now the course is with 15% offer. Okay, so if you are interested, or if you or your sisters or brothers or your neighbors are interested, please check the things with the while referring with this number 8129 000 700. If you call these numbers, mentors will be available, and you can check the course details with them. And I'm having also another 2 courses also, Thalapathy and VETRI. So Thalapathy is for 12th preparation students. So if you are in 12th standard and if you are wish to take NEET preparation in your 12th standard itself, this batch will be your apt batch, and we are having repeater batch for VETRI. So in this repeater batch we are having live sessions as I said for fast track. We are having live sessions, we are having recorded sessions, we are having previous questions and personalized mentorships, and we are having all India test series and also graded in battle, everything with 14,000 less than 14,000, which means 13,649. okay, so please do check with the this free number, this number 8129000700, and this mentors will be guiding to any of the batches details. Okay, if you are our offline centers are available at Trichy, Tirunelveli and Coimbatore. If you are nearby to these centers, just visit our centers and you can enroll your admissions if you are needed. Okay, so we have seen these chapters as a holistic. Okay, if you want your if you want this notes, handwritten notes, you can just scan the thing, or else you can also check the things, check the link in the description, and there you will be finding some WhatsApp group, and there the every notes are available. So thank you so much. If you are having any doubts, just put it into the comments and I will be addressing. Thank you so much and wish you all success in your life. Bye.